then it drops to 1/64. Then after delay in 4 samples, you see that correlation stays the same. It doesn't change anymore. So after this task, we discussed another one. We just considered filter triangular transfer function, and we tried to analyze what happens if we pass white noise filter. And of course, you remember that original white noise is limited, so it goes from minus infinity. But after you pass this noise band limited system, also becomes band limited. And we saw that resulting power spectral density will be defined by transfer function and times original power spectral value of power spectral density. Then we have found correlation. It's not delta pulse anymore, be wider, and in our case it was defined by C function. Afterwards, we calculated RMS value. What's the variance of output? What's the variance of output after this filter? And you remember that if you don't anything, then RMS would be infinity because you have unlimited. But after pass your signal through filter, F filter, then you get our RMS, our variance, depend not only on variance of noise, but also on bandwidth that we have. Larger bandwidth, larger RMS value. And also we discussed another example, similar. So we considered the filter given by channel impulse or by. We also had the same power spectral density for. We calculated output power spectral density, and we found it was cutoff frequency as function of we had to find RMS as function of cutoff frequency. And first of all, we represented what is cutoff frequency, how it depends on parameters of our filter. Found that cutoff frequency inversely proportional to duration of our impulse response. Then we calculated RMS value, and then we could express RMS value in terms of cutoff frequency. And you see that again, that larger cutoff frequency, larger RMS value you have. Result from last time. And today we're going to continue. Yeah, other any questions? Not, then we continue solve our tasks. And we go to task number 4.7. Try to analyze how to think this, how to solve this task. Okay, we consider the following modulated signal. We have signal x of t equals to summation and goes from minus infinity. Minus n capital T. Of t is our pulse shape function, z of n sequence of symbols. And we can decompose, we can separate these two parts. We can say that this summation of pulses we can represent as convolution between pulse shape function and sum of symbols that we transmit, or sum of delta pulses that weighted by transmit symbol. N times delta minus n capital T. So we change magnitude of each delta pulse according to amplitude of symbol that we transmit. And the part that consists of delta pulses, we denote as x delta. Our signals we transmit, but it has it's represented by delta pulses. And in order to make it feasible, we have to substitute each delta pulse by pulse-shaped functions that we have. So, and we assume that we have a finite alphabet. We assume that alphabet 0 contains 4 symbols, -3, 1. So we have 4 symbols, and all of them, they have the same probability, equally like the same probability to appear in our stream of data. And also we say that neighboring symbol is statistically independent. And these two assumptions allow you to simplify all equations. So we also say that our pulse shape by the function, by rectangular function, equals to u times rectangular e minus divided by capital T. And I also recommend you to try to solve the same task at home, but with slightly different pulse shape function. Try to solve this task for the pulse shape function represented by times rectangular minus T divided by capital. And say that much larger 1 over T. And here we consider this task when you have just rectangular pulse without additional sine term. So what else we know? We know the modulation of or symbol inter. Okay, now let's try to solve tasks that we have. First of all, we need to draw autocorrelation function for phi zz of m of the discrete time process z of find phi zz. And it's actually my question to you. What should we do? Solve to find autocorrelation function of a discrete sequence of symbols. Are there any ideas? Have a discrete sequence of symbols z of n. Z of n has 4 elements in the alphabet. Then my question, so what should do to calculate autocorrelation of this discrete sequence? Sorry, table. Maybe you can use microphone, and but don't forget to unmute it.
By putting it into the table, these symbols, and like multiplying and summing it up.
But yes, I mean, we previously we did it. We wrote it in a table, but it was for the case when we had fixed sequence. I mean, our sequence of symbols was fixed. But here you have sequence itself undefined. So I can just show you arbitrary sequence. At each of 3 possible amplitudes. Oh, 4 possible. Don't know. No dependency between what goes with the next element. We have this random sequence.
Since use of moments.
Exactly. Yeah, we should use moments. Yeah, we say that they independent, and we say, and as a result, we can, when we calculate autocorrelation, we need to use moments. And when our example for sequence of n. Minus 1, 1, minus 3, 1, minus 1. And then we say that if we want to calculate autocorrelation function, sequence z, we have to calculate for L equals to calculate second moment for L equals to 0. And you calculate first moment first for L non-equal to 0 because you assume adjacent symbols independent. That's what we do. And I can just I can show the following. This is our original sequence. So if I shift this sequence by 0 samples and multiply element-wise sequences, what will happen? See that we just take each element in our alphabet and calculate square value of it. And then we calculate average. And as a result, L equals to second moment. And in order to do this, just take probability of multiply by square value of it. At square value for real valued constellation. If you work with complex valued signals, then you have to take norm of it, or absolute value squared. 1 over 4 squared, 1 over 4 minus 1 plus 1 over 4 times 1 squared plus 1 over 4 times 3. This is our second moment. And we just need to calculate what will be the result. So it will be 9 plus 1 is 20 divided by 4, 5. L equals to 0, we have result equals to 5. Okay, fine. Now we need to do another step and calculate what will be the result when L non-equal to 0. And what happens actually when L non-equal to 0? I just visualize copy. Right, was before L non-equal to 0. First picture was 0. On the left, on the right, sorry, for other shifts. So let's say just we by one sample. And then, again, you shift your sequence by 1. By 1, by 2, by any number. And we calculate element-wise product. And you see that actually there's no dependency between what will be the possible pair of symbols and taking into account current pair of symbols, you cannot predict anything about next one or previous one. As a result, this element-wise product, and these two random variables in element-wise product, they completely independent. As a result, we say that we just calculate mean value for first variable and mean value for second random variable and calculate result. What we have to do, we have to take value of our alphabet, 1 over 4, 3, times 1 over 4, 1 over 4, 1, plus 1 over 4 times minus. And because this our alphabet is balanced, yeah, you have same number of positive numbers as number of negative. Result mean value will be 0. Don't have. And based, yeah. And now we can plot our resulting autocorrelation function for this discrete sequence of symbols. So as a result, we have only one non-zero value at 0. All other values, discrete indices, we have 0. Why? No, sorry, it was M, because M is shift. But original sample was M. Okay, and we have at 0, we have 5. And then we have for all other have 0. 1, 2, 1, minus. This is our discrete autocorrelation function. And we did it first tutorial when we start discussion about acoustic signals. So next, we go to part B, and there we need to draw P of t find its energy. So, and now we need to find energy and original signal angular pulse divided by capital. Very easy to plot because angular pulse. Goes from 0 to capital T, has amplitude function of time. And now we need to find energy. And of course, you can easily find energy, but also I prepare homework because energy expression for energy find it, but for rectangular pulse that we have here, so we just calculate square value of our signal and we integrate over its duration. And then if we substitute, we have integral from minus infinity to infinity of rectangular function squared minus t of pi by capital T times dt. And then if you just apply this duration of rectangular pulse to limits, then you can say that you need to t. And as a result, we can write that it's u. And it was, you could just look into this figure, you could already say that energy will be times amplitude squared. But okay, and then we need to determine autocorrelation function. But I will show you difficult way how to find it. Not because you don't know, but just to give you another option how to find autocorrelation. So we're going to use the following chain. First, we have signal time domain. Then we're going to find spectrum of our signal. Spectrum, we're going to find energy spectral density. And finally, from energy spectral density by inverse Fourier transform, you find energy autocorrelation function. Energy. So, and now let's start finding autocorrelation function. But of course, you know that for rectangular pulse, autocorrelation function will be triangular. But you can use this hint if you have more difficult waveforms to analyze, because it works perfectly for rectangular pulse, and it also works fine for other functions. So, first of all, we have rectangular pulse shape. P of t equals times rectangular pulse minus capital T divided by capital. Then we perform first formation, go to frequency domain, and we find spectrum of signal. 0 times t times c function f capital T times exponential function minus j I f t over 2. Just our basic transforms that from rectangular pulse we get c function in frequency domain. And also we use the property that if you have delay in time domain, frequency domain, you will have additional phase for each subcarrier. So, and okay, fine. Now we need to find energy spectral density. And you remember that energy spectral density can find by calculating product between room and conjugate of it. P of f times P of f conjugate. What happens if I take this signal f and multiply it with conjugate of it? What will be the result? But what will be the result? Or maybe you can use microphone also.
U square of and t square.
For t squared?
C square pi f t.
Okay, but what happened to exponential?
1.
Why?
Complex conjugation. Exponential.
What happens with complex conjugate of exponential? So instead of minus, we have plus.
Yes.
Yeah. And if you take, correct, thank you. If you take complex exponential and calculate conjugate, change sign. You have exponential j pi f. Then you have one term minus j pi f t over 2, and another term with plus argument, positive argument, plus j to pi f t over 2. As a result, if you multiply them, it's 1. Don't have any exponential term power spectral density in energy spectral density. correct? And now you can find autocorrelation function by calculating inverse Fourier transform for energy spectral density. Write that our autocorrelation function can find. And you remember that for C-square function, inverse Fourier transform will be triangular function. Have U times T times triangular function. Now we tau over capital T. That's all. That's it. And going to from frequency. Okay, and you see that we get already known for us a result that it's just U squared times T times triangular function. But again, I have shown you just to demonstrate that you can also use this trick for more difficult cases. Okay, what next? Questions? Yeah, are there any questions? No, it doesn't work.
Sir, won't be it
Yeah, sure, of course, it should.
triangular pi this sorry
It was
tau upon 2t,
I
sir.
could hear you very well previously, but then something happened and I don't hear you anymore.
Sir, I hope my voice is audible.
Doesn't
Hello.
work. Check, I think.
Am I
something has
audible,
been-
sir?
Yes. As you write it as model absolute value squared, actually it's the same expression. If you take absolute value of f squared, you can write it as product between p of f and p of f conjugate, because it's definition of absolute value squared, definition of norm. Okay. Unfortunately, we question, and if it was this question, please let me know. Write in the chat. So now we go to But remember that when you have triangular function, and we can also check it in our cheat sheet, yeah, that equation for triangular function is capital T. And we write that it's rectangular over capital. But for triangular function, 1/2. And we say that triangular T over capital. And of course, the whole duration. Because there is triangular T over 2T, but according to our, yeah, probably it also it depends how you introduce, but in our course, say that triangular T over capital T equals. Yeah, I recommend to check these basic Fourier transforms that we have, this table of basic Fourier transform that we have in our Moodle web page. Okay, so let's go further and go to part D. Part D. Where's part D? Yeah. And I think there is a typo because we need to. No. Of course, it's written autocorrelation function of x delta t and x of t, and we need to specify figure and equation, of course. And also, you already have hint how to find autocorrelation function, not only for discrete time sequence of symbols, but for continuous time sequence of delta pulses. And actually, it's very easy to get. What should you do? You should take your sequence, you should take your discrete autocorrelation function and normalize it by period. And instead of each discrete delta pulse, instead of each discrete pulse, you substitute delta pulse. Let's try to. And let's say that now this autocorrelation function, continuous time autocorrelation function of our sequence of symbols that contain delta pulses as 1 over capital T, m minus infinity pi z times delta pulse, and then we have tau minus capital T. So we have to take each value for our discrete time autocorrelation function and replace it by delta pulse. And while we replace it by delta pulse, we also have to normalize magnitude by 1 over t and value of this autocorrelation function itself. What happens if original time autocorrelation function pi z m was only one non-zero discrete pulse at origin, amplitude 5, and 0 elsewhere. When we expand it to continuous time random process, following, say that, okay, or it was autocorrelation function of discrete index, now autocorrelation function of delay. But this continuous time autocorrelation function will contain delta pulses. It will have delta pulses. In this case, in this specific case, you have only one delta pulse at origin. Because what you do, you take this pulse at 0, then you multiply by corresponding delta pulse, 0. That you get delta pulse at 0, and you have to take original amplitude divided by the way, what is T? What is capital T? Of what? It is duration of our symbol. Duration of our symbol. Because I think later we have more interesting example where we have we'll have two different time intervals. We have smaller time interval for talking about. So here we have to say have magnitude for time autocorrelation function at 0, 5 over capital T, and it's represented by delta pulse, and 0 elsewhere. Say that it's autocorrelation function sequence of delta pulses created by transmit symbols. So this is what we get. So now we have autocorrelation function for x delta tau. And the last step that we have to do, we have to write, or we just have to recap that if your original can be decomposed for two parts and represented as convolution of these two parts, autocorrelation function also can be represented as convolution of autocorrelation function for each part separately. Say that autocorrelation function of xx of tau can be written as autocorrelation function for pulse shape, autocorrelation function for sequence of delta pulses, delta x delta tau. And we already know all these parts. So you know, right, it is phi convolution with over 5 over times delta pulse at 0. Can I further simplify this expression? Can I somehow get rid of delta pulse? You come louder? Sorry? Yes, but you have much easier. You don't need to use Fourier transform. And what will be the result? Yeah, I mean, it's because this delta pulse centered at origin. Whatever you have, whatever signal you have, convolved with this delta pulse, it will be the same signal times magnitude. As a result, you can write it will be phi tau times 5 over t. Because it's just one delta pulse centered at origin. And what's the autocorrelation function? What autocorrelation? Autocorrelation. Pulse shape. Minus t capital T has maximum value per times t. Okay, and now we need to calculate, no, we don't need to calculate anything. We just say that resulting autocorrelation function 5 over times triangular function tau over capital T. And you see you have 5 squared times triangular function tau over capital T. And we can also make a plot. But I mean, it's function with specific goes from minus t. And it has maximum value 5 using ixx of tau. Okay, this is, I think that's all. This is the whole task 4.7. 4.7. Are there any questions? No. Determines the power spectral density of last step, it was E, and then we need to find power spectral density Ixx. Okay, there is nothing to do because if you have autocorrelation function as 5 times U now over n. Perform Fourier transform. Get that energy spectrum. Sorry, not energy spectrum. Power spectral density. It was for pulse shape. Power spectral density 5 times t times C function phi f capital T. Phi f capital. And okay, you can also draw this apart. And draw the C over T and so on. And show that it's smooth function without any sharp transitions. It's slowly decreasing. 5 times T. This is maximum value. Our power speaker desk. What else? That's all. That's all for this task. Can go further. Okay, now we go to, if you don't have any questions, you go to task 4.8, next task. So, and we have more interesting signal for task 4.8 because it contains also alternating part. So every next symbol will change sign. So, and we have L, summation, n goes from minus infinity, minus 1 power n times b of n times p subscript L minus n t. And as before, we can separate two parts or represent it as convolution of two parts, pulse shape, p L of t, convolve it with some goes from minus infinity of delta pulses. 1 power n subscript n times delta pulse n capital T. Our original signal. And we say that we have a finite alphabet, b of n belongs to one of two options, 0 or 1. And both bits equally, because they have the same probability, appear in our data stream. Neighboring bits statistically independent, okay, also as usual. And also we say that pulse shape or low pass representation of our pulse shape function given by the following expression. PL of t equals to times rectangular pulse shape function minus capital T over divided by capital T. And in addition, we have a phase term, exponential j pi over 2. Okay, great. And we have 4 questions. Well, let's start with the first one. We need to determine autocorrelation function of x delta t. What is x delta t? Say that this sequence of delta pulses as x delta of t, delta pulses, and we need to understand what will be the continuous time autocorrelation function for this sequence of delta pulses. Okay, and what should we do? What will be the easiest option? What should we do to find this continuous time autocorrelation function? I just want to remind you that in previous task, we already found it, all the steps, and I just want to make sure that you understand what's our procedure, how you find time autocorrelation in general, not task, but in general. And it's not difficult. You have, for this sequence of delta pulses, you in general have two parts. You have a discrete sequence of symbols, and you have delta pulses. So your algorithm is the following. First, you have to find autocorrelation function. You have to find discrete time autocorrelation function for sequence of symbols or bits that you have. And then you extend this discrete time autocorrelation function to continuous time autocorrelation function by replacing all discrete pulses by delta pulses and weighting them or dividing them by duration of your symbols. I mean, we did this in task. So it was here. First, we found this discrete time autocorrelation function. Then we, yeah, actually we can see it here. Then you just normalized, divided all amplitudes by duration of symbol, and you replaced all discrete time pulses by delta pulses. This is how you, this is like this very simple indication of what happens behind. And we do just the same, we have to do the same here. But here we have something more interesting. We don't have just a sequence of bits, but we have this also sequence of bits that depend on current index of n. But in general, it's still the same. You can just say that this combination of -1 power n and b of n we denote as. And we just then we just need to do the following. First, we find autocorrelation for b of n. Then we find autocorrelation for z of n. Next, autocorrelation for x delta. And finally, autocorrelation for the whole signal, taking into account that we know what the autocorrelation for pulse shape. I mean, not difficult. So, and yeah, let's get started. And my first question, okay, not the first question. I don't know what the number of this question, but we need to find autocorrelation for sequence of bits. You should know how to find it. Have to. No, you must know autocorrelation for sequence of bits. Yes, there is nothing. Just you say that second moment m equals first moment squared m not equal to 0. And what will be the second moment? So it will be have for 1 by 2 times 1 squared plus 1 by 2 times 0 squared over 2. And and what will be the for non m 0. Same.
1 by 4.
By 2 times 1 plus 1 by 2 times 0 squared. 1 by 2, 1 over 4. Not the same. So, and we have, yeah, we can, now we can plot this autocorrelation. So at 0, we have value 1 by 2. Then for all other values, we have 1 over 4. By 4. Our autocorrelation function. And it's only one part. Now we need to find autocorrelation for sequence, for alternating sequence of bits. So we have alternating, but it's sequence that multiplied by -1, one with different signs. So we have phi, z. And in general, we can use the same idea second and first moment, but easier it will be show if we just write definition of autocorrelation. For definition of autocorrelation, we say that autocorrelation is expected value of product between original sequence n and shifted version of this sequence, shifted by m samples version of this sequence. Have real valued sequence of bits, so we don't need to place conjugate. As a result, if I write what is definition for z of n, and remember that z of n previously was the following. It was -1 power n times b of n. This is how we define, how I have defined it. 1 power n times let's put this value. -1 times b of n, b of n times -1 n plus m times b. I can slightly arrange components inside expected value. Actually, I can do the following. -1 times n is deterministic quantity because it just depends on index, but there is nothing to average. As a result, I can rewrite it as -1 expected value of times b of times -1 plus m. What is expected value of b of n times b of n plus m? It's not necessary. Second moment. What if you put different m, m non-zero? Yeah, there is more general. It's autocorrelation function. There is more general definition. So this is nothing else as how autocorrelation function is defined. It's expected value of one sequence times shifted version of sequence. So this is autocorrelation of original sequence of bits. It's function of m. And can write also what I do else, I also combine these two parts, first and the last one. So we have -1 plus m times autocorrelation function. And also, if you look to the power of -1, there is term 2n. And if you have 2 times any number, this quantity always will be positive. You can just drop it. And as a result, we can write this autocorrelation function -1 power m times I m. So this is how it looks like. Now we need to try to visualize this result. Let's do it step by step. First of all, I will copy original autocorrelation for or original autocorrelation. Then I will show the b minus 1 function of m. 1. If m equals to 0, then we have minus 1, minus 3, and so on. So for 0, we have plus 1. For 1 and minus 1, we have minus 1. For 2, we have 1. For minus 2, we have 1. And see that you have this alternating sequence of 1. I mean, sign is alternating. Plus, minus, minus. So, and now we need to multiply these two sequences, original autocorrelation function and this sequence of ones with different sign. And do this, see what we get. So at 0, we have 1 over 2 times 1. It will 1 over 2. Then at 1 and minus 1, we have minus 1 over 4. At 2 and minus 2, it will plus 1 over 4. And we can just function. Those are. One minus function of m. This is how our autocorrelation function looks like. The problem is that we need to somehow formalize this autocorrelation function to calculate pulse density or to make meaningful conclusions. Yeah, we need to somehow formalize this autocorrelation. And there is very interesting way how you can do this. You can see, or you can treat this sequence of one from sine as sampled version of sine or cosine function. Because you remember that if you take a cosine function or whatever function you have, and sample it, and then depending on your sampling frequency, you can have like this. You have plus 0, minus 1, 0, plus 1, and so on. Or you can sampling frequency over, you can just take samples at maximum and minimum. Then we can say that this sequence of alternating samples, nothing else as just sampled version of cosine, just cosine. And understand, because in order to define cosine, you have to specify a period of this function. Period of this cosine function, or I can even our sine. This green, green pulses, they nothing else as these samples of this cosine. But something happens, something wrong happens at origin, at 0. Because, we just consider this pulse at 0 as two components. One component belongs to cosine, and then another component just on its own, just remaining part of pulse. Yeah. I think we already did it. Have this remaining part that will stay on its own. We just keep it as some constant. Okay, but we still have to understand what to do with this cosine. We have to somehow introduce this cosine. And this function must be function of index m. So let's try to write. We have cosine phi times c. At every next sample, our cosine changes sign. I can just put m as it is. If I place m like this, what will happen? I just like phi times m. When m equals to 0, 1. When m equals to 1, what's the result for cosine 2 pi m for m equals to 1? It's again 1. And for m equals to 2, 1. Okay, we have our step is too big. We have to reduce our step. Let's try to reduce it by 2. So if m equals to 0, then we have 1. But what happens if m equals to 1? Minus 1. And for m equals to 2, 1. Okay, so it looks that it's exactly what we need to get. So we have alternating sequence, 1 minus 1. And as a result, we can keep it like this, but then we can just divide it by 2, and as a result, we have pi times m. But in this form, it's also, we can just keep it. Okay. Let's try, it was function. Functional. And rewrite it as, what was autocorrelation? 1 over 2. We can now formalize it and write it as 1 over 4 times cosine pi m over 2, alternating part. But we shouldn't forget the remaining part at 0, plus pi. How should we? I will write 1 over 4. I use these square brackets to denote this pulse. Just to denote that 0, we have this additional term, 1 over 4. So, and this is how we can write our autocorrelation function. Yes. Don't have discrete time. Okay, our cosine looks like continuous function. It's true, yes, cosine is continuous function, but discretization process is performed by taking specific values for m. M is integer value because it's difference in number it's integer difference between indices. And as a result, you never choose any other values for cosine rather than these specific points. Yeah, I agree that we used continuous function to represent discrete time process. But because we choose only specific points, it's fine. Because m always integer, and as a result, I mean, in general, you're not allowed to take any fractional m. It always will be minus 1, 1, 2, 3, 4, and only integer value. As a result, cosine, you have this value that we need. But it was actually a good point that careful about it. Okay. Yeah, and now it was, so let's see. I can say that when we were working with beats, it was first step. Second step, when we extended to this alternating of symbols. And third step, because our goal is to find autocorrelation function for x delta t. It's continuous time. Now I write from previous task that continuous time autocorrelation function for sequence of delta pulses. And write as 1 over t, and then we have summation m. M goes from minus infinity pi times delta pulse now minus m capital T. So, and what we should do? We should replace everything what we have there and write that our autocorrelation function can write. First, what I'm going to do, I'm going to write this autocorrelation function as function of this alternating ones and ones. No, should we? No, we're still talking about part A. Still trying to find the autocorrelation function for x delta t. Because what we say that we have this x delta t part. And in order to find autocorrelation, we have to do steps. First, we have to find autocorrelation for b of n. Then we find autocorrelation for z of n. And finally, we find autocorrelation for x delta of t at the last step of part A. We write it as write it as 1 over minus 1 times pi. And then we have delta pulse, capital T. Okay, and now we try to replace cosine. So we try to replace sine, and we can write it as 1 over capital T. I should 4. 1 over 4 capital T. M goes from minus infinity. Then we have cosine pi m over plus 1 over. Okay, let's split it because I don't want to keep it time. Times delta pulse tau minus m part. And for continuous part, say plus 1 over 4 capital, no, 1 over 4 capital T times, and we have delta pulse, tau minus, or I can write just test. Okay, this is our expression. But the next question actually will be to find spectral density. Out for part A, have expression. But let's do one more step, because you remember that it's much easier to calculate power spectral density, have sequence of delta pulses and pure signal. without any delta pulses. But here, we have problem. Cosine is inside this summation. And what you want to do, we want to move outside this summation cosine and represent this part as convolution between continuous time cosine and sequence of delta pulses. Yeah, do you understand this problem? Cosine function is inside. And at the next subtask, when you need to calculate power spectral density, you have to calculate Fourier transform of this cosine function together with delta pulses. This is not trivial, but it's much easier to calculate Fourier transform if you have cosine outside, convolve it with delta pulses. And then you know that for cosine, Fourier transform will be delta pulses. For sequence of delta pulses, Fourier transform will be another sequence of delta pulses. Okay, anyway, now we have to somehow move outside this summation cosine. And when we do this, when we move cosine outside summation, we have to change discrete time to continuous time. So this cosine must become function of delay and sample capital T. Right. Yeah. Oh, could you please use microphone?
I'm just asking, I don't understand the last statement of 1/4t with the delta impulse without the shift.
Yeah, this is just the last part, because you have 1/t delta at 0.
Yeah, but this multiplied with the delta with tau minus mt.
Yeah, but it's just, I mean, it's discrete pulse. It's just like discrete pulse. I mean, it's just pulse with amplitude 1/4.
But it's not multiplied with the delta tau minus mt.
And what happens? Yeah, what happens? I mean, this is delta pulse at origin. This is delta pulse at origin. There. Don't believe me, but you have 1/t. And then for your discrete time delta pulse, you substitute 1/4. Have this. Don't write actually that it. Have this expression for our continuous time autocorrelation function. And you take value for discrete time autocorrelation function for m equals to 0. For m equals to, and what's the value? The remaining value. 1/4. So it's pure value of this discrete time autocorrelation function. Without any additional delta, without anything, just amplitude. 1/4 times this second part, delta pulse, and then what's the value of m? 0. So it will be delta tau minus 0. But it's the same as if I would write as just delta. Or I can write it as 0. So these three notations equivalent. Tau 0 or tau minus 0. Okay, maybe I write instead of tau, I will write it as 0. We have that at 0, we have this term. 1/. But the question was how to move outside cosine, because now it's function of index m, but after we move outside summation, it must become as function of duration and delay. Okay, let's
exponential
just
form.
do it. Oh, I think there's someone open microphone. Are there any ideas?
Yeah, cosine into exponential form.
can do it, but you can also do it much easier. You can just do directly on cosine. Just do directly on cosine. And how you can do this? You can okay, we do the following. That I just make another. I show this alternating of whatever we have. Plus, minus, plus. But it was actually a good point because we can also, if it will be longer, but it will work because you can just represent cosine as exponential term and represent it by exponentials. And after you replace it by delta pulses, you see at the position of delta pulse, instead of m, we place t. It's simple iteration. So we have first sample at 0, second at second one at third one at 3 minus 2t. Now we place our cosine function. So cosine function. And need to answer the same question as before. What's the period for this cosine? Period is equals to 2t. So we can write it. We have sine phi equals to 2. Have something divided by period. And that's all. That's all. If yeah, practically, but that's all. That we just need to specify period and just divide by it. And now we just need to perform self-check. Yeah, that if we choose for tau, if tau equals to, then the result will be 1. Tau equals to capital T. What will be the result? Minus 1. Finally, we have 2t. Result will be again 1. So that's all. You just need to plot your desired function, determine period, and write what will be the cosine such function. That's all. And now we can rewrite our expression as 1 over 4 capital T times cosine phi tau over 2 convolution. Actually, I think it's better if we also have it's fine. We don't else. Just write that we have summation delta pulses. M goes from minus infinity. And we have delta pulse tau minus m. Just a sequence of delta pulses without any magnitudes. Magnitude will be 1 to each delta pulse. Plus, we also have remaining 1 over 4 capital T times delta pulse at 0. It's our result. And the resulting autocorrelation function for x delta. Continuous time autocorrelation. And it help us to find what we need to find. Energy, no, well, it's B, we need to determine energy spectral density of pulse shape. At third step, it will help us to find spectral density for the resulting signal. Actually, I think we should don't ask us. Later on, they will ask us to find pulse spectral density for the whole signal. So let's find autocorrelation function, pulse spectral density such signal. So you can write that fast packet density delta x right defined as product fast packet density for first part, fast packet density, energy spectral density for part, and fast packet density for second part. And right, that is 1 over 4, 1 over 2. So f minus f minus 1 plus 1 over 2 plus 1 over cosine. For cosine, we have 2 delta pulses. Okay, and times. And then we have sum of delta pulses. And we also have Fourier transform. Just need to normalize by spacing times 1 over capital T. Goes from minus infinity. And we have delta pulse minus 1 over capital T. Our sequence. Okay, fine. But now we need to calculate what will be the result. And I ask you, do you know what will be the result? Can you simplify this expression by just looking on it? And by the way, I forget faster. Plus 1 over. Okay, no problem. If you cannot simplify the expression, then we have to do it together. And in order, I will do it graphically. First, I will show how original sequence of delta pulses after Fourier transform looks like. And then we try to figure out what we should do when we multiply these 2 delta pulses. Okay, original sequence contains delta pulses weighted by 1 over t. We have delta pulse at 0. And then we just continue plus infinity and to minus infinity. The sequence that we denote as, let's say that it's 1 over t, goes from minus infinity, delta mu minus f minus mu 1 over capital T. So, and this is our sequence. And then the following. By the way, what this thing is 1 over T. So, and let's multiply this sequence with first term, first parenthesis. 1 over 2 delta f minus t. What should we do when we multiply delta pulse with another delta pulse?
Frequency shifting property.
1 second. There is not convolution, it's product. But if we evolution, then we would have to replace each delta pulse by the whole side. But here we have evolution, but not product. Now it's correct. Because I see product between delta pulse will be 0. And now, yeah, sorry, it's convolution, not product. I mean, it's not difficult. If you calculate convolution between signal and delta pulse shifted by specific value, you just need to shift this signal by this value. Shift it by 1 over 2t to the right. And when you calculate convolution to delta pulse plus 1 over 2t, then you shift it to the left. That's all. And shift it by 1 over 2t. And also, we divide magnitude by 2. As a result, we get the following sequence. Or shifted by 1 over 2t. Our sequence that we denote as delta f minus 1 over 2. F minus mu 1 over t. Our first part. For the second part, do something similar, but we shift to the left by value 1 over 2t. 1 over 2t. But surprisingly, we get exactly the same sequence as before. Because spacing between delta pulses is 1 over t. And if you shift one sequence by minus 1 over another one by 1 over us, and you will get exactly the same sequence. Because it's infinite. F plus 1 over 2t. Delta f minus and then you calculate sum of these two sequences. Have one sequence shifted to the right, another sequence shifted to the left, and what will be the result? You can just choose any of these two sequences. Just write. We just write it as what? Right. Expression for it. As a result, you have pulse. You have times larger than this. What will be the magnitude? 1 over t over t. Also, we shouldn't forget the whole expression. We have 1 over 4t, but we add it later. Sequence, right, has 1 over t goes from minus infinity. Then we have delta pulse f minus 1 over t. We have additional shift by 1 over 2t. Or we can write plus of 1 over 2t. Doesn't matter. This is the result for solution. Only part of power spectral density. Also say first. Delta F plus 1 over. Then we get this resulting result. Now we can write it. Our power spectral density F right as 1 over 4t part plus 1 over times summation goes from minus infinity minus 1 over t minus 1 over our power spectral density for the sequence of delta pulses, weighted delta pulses. Okay, but it's all was about part A. Are there any questions? Okay, if not, then I think we can go to part B. Part B, we need to determine energy spectral density of PL of T. And there, where is our PL of T? L of T times rectangular pulse shape minus T divided by capital T, our rectangular shape function, times phase I over 2. And we need to find the energy spectral density. And we just use the same procedure as we did in previous task. Just start with L of T, then we find PL of F, power signal, and from spectrum we find energy spectral density. This is what we do. And our calculate Fourier transform. And it equals to times T times psi function phi f capital T times additional phase because of time domain minus j pi f T and times original phase term that we had before, pi over 2. See that these two terms that we have at the end is phase of our, just phase of our spectrum that we have. And as we also discussed previously, if you have any phase for your spectrum, after you calculating power, energy spectral density, you just get rid of this phase and you keep only magnitude. As a result, calculate energy spectral which is L of F times L of F conjugate, and write it as rho squared times T times psi squared pi F capital T, and nothing else. This is the resulting energy spectral density for our pulse shape. Okay, fine. And now we go to part C. Go to part C, and part C we need to find power spectral density XL, XL, F. Yeah. Microphone? Where is my?
We need to actually write the figure for B.
Do we? Okay, yeah. Oh, thank you. Ah. Catch at me. Yeah, before we go to part C, we actually have to plot the energy spectral density. Point. F. And there, what we have amplitude and zeros with positions 1 over t and multiples of it. 1 over t. Over t. And have to again show psi squared. That is smooth. But again, show it approximately. Have to specify maximum amplitude. This energy spectral density, function of frequency. Now I think that's all for this part. And we still try to do it. That's C part. Determine power spectral density XL, XL of F. But I mean, we don't need to calculate anything because we already have everything what we need. We can just write that power spectral density. Nothing else as product power spectral density, sorry, energy spectral density for L, function of frequency, times power spectral density for x delta, function of frequency. And we know both parts. As a result, we can write that resulting power spectral density for signal in low pass range is, careful about scale, 0 squared times t squared times psi squared of pi f capital T. And now we write what we have for x delta. I copy. And times power spectral density for x delta. What we can say about this power spectral density? It will contain two components, two parts. You look, see that we have first part continuous over 4 squared t over 4. Yes, it's correct. Times psi squared pi f t. This is continuous part. In addition, we have second part, discrete, because it's represented by delta pulses. So we have u0 squared over 4 times psi squared pi f t times summation goes from minus infinity, delta pulses f minus mu 1 over t, 1 over 2. Okay, and finally, show this plot for this function. Okay, and Okay, we have first part, continuous. This one. I mean, you see, in general, because for continuous part, it's t times larger, I just to show that it will be higher on our plot. But you can, it's not necessary, you can actually just choose any want. Just to have enough space for discrete part. Show it like this. This continuous part of our spectrum because it goes further. So, and in addition, we have discrete part. Let's show it. Oh, I show this dashed line because don't have this envelope. Instead of this envelope, you will have scaled delta pulses. And these delta pulses, they placed at 1 over 2t. Zeros for original C function we have at 1 over t. 1 over t. 1 over t. For delta pulses, have they place it at positions 1 over 2t, then p over 2, and so on. 5 over 2t. Have delta pulses. Like this. So, and you see that, okay, I don't, not sure that absolute scaling for delta pulses is correct, but at least you show that magnitude defined by envelope of C square function, and they have specific position. Minus. And we can also say that for green line, maximum value will be squared times t over 4. And for purple line, maximum will be times 1 over 4. At all. And this is a function of functions of. Okay. No, we don't have any more. But you can, at home, you can also try to plot the power spectral density of bandpass signal. What you should do, just should recap material that we discussed at first tutorial, that if it's your low pass signal, and if you form bandpass low pass transformation, then just move one part to positive range, another part to negative range. We have to, because we increase energy, we have to divide by square root of 2. Whenever you have amplitude, you have to divide by square root of. That's all. It will be your bandpass signal. But I mean, this is just a sketch, yeah? But then you, at home, you need to plot it explicitly. Show. If you have real value signal, then you just multiply by cosine. If you have imaginary signals, then you multiply by sine. This is what we do. Okay, are there any questions before we stop our tutorial? If not, then I would like to say thank you for your attention. Starting from next week, we have online tutorials, and I will send you link later this week. And yeah, and then if you don't